speaker is also Özdağlar from MIT, and I don't want to steal any more of her time.
Thank you very much. So thank you very much for inviting me. This is a wonderful workshop, and today I'm going to talk about a very recent work, recent paper we completed on a variation inequality framework for network games, and this is joined with a brilliant researcher, Francesca Parise, who's sitting there. She's a postdoc in my group at Leeds, and I'm from the Department of ECS. So network games, I guess the connection to the workshop is the network games. It's a general framework for analyzing social, economic, or let's say societal networks, also those with an infrastructure underneath. And the goal of the paper is to show that the variational inequalities, basically, this approach is a unified, systematic, and powerful approach for analyzing network games. And I'll try to show you basically how this unifies many of the existing results in the literature. So just to motivate, in many social and economic settings, clearly who interacts with whom matters. For example, if you think about the decision of an individual to buy a product, adopt new innovations, ideas, behaviors, our decision to smoke, for instance, or form opinions, contribute to public goods is all affected by the actions of our friends as well as acquaintances. And similarly, in the context of competition, if you think about firms' investments, these are also affected by other firms producing substitute or complementary goods. And sort of over the past decade or two, network games have emerged as a powerful framework for analyzing such interactions, whereby agents interact with each other according to an underlying network represented by a graph. And the difference of this game model from general games is that players' payoff does not depend on the strategies of everyone, but only of his own action and an aggregate of actions of those in the neighborhood. So somehow this is sort of summary statistic, and it only depends on the actions in the neighborhood. And because of this aggregate property, sometimes these games are also referred to as network aggregative games in some of the literatures, but it's the same idea. And the major interest of this literature has been how the underlying connectivity or the patterns of interactions, how sparse this network is, how clustered this network is in shaping the equilibrium outcomes. And if you look at the literature, there's a large literature, and this is, in several different strands. I'll try to point out these. This is mostly in the economics. For tractability reasons, much of this work focuses on special games. And what do I mean by that? Games with specific structure. They assume that the cost functions are quadratic, scalar, they're non-negative, and mostly symmetric networks, meaning that I influence Francesca the same way she influences me. And moreover, the focus has been, this is also an important point, has been on specific types of interactions. So games with strategic complements or games with strategic substitutes. And what that means is basically high level, best response of an agent is increasing in other agents' strategies in the case of complements, so the strategies move in the same direction, or decreases in other strategies in the case of substitutes. And there's a large number of papers here. I just put sort of some of the seminal papers in these two different settings. Just to put it into context, I think I just want to give you an example. Think about, for the complements, maybe investments in new technologies. Let's say farmers invest in a new crop, making it more productive. That increases other farmers also adopting this new crop or new technology. And for the case of substitutes, sort of an example that sort of rings a bell is the context of security. If a set of computer networks or systems invest more in security, that makes an attack being successful less likely, and therefore discouraging others to make similar investments. So that's a case of substitutes. But if you look at a lot of economic interactions or strategic interactions, we don't see this substitute and complements. Both effects are present. And moreover, another important thing to notice in this literature is within these assumptions, works relied on disparate techniques, mostly through some potential game, potential function characterization, but then led to different characterizations of equilibrium. Some like if you look at Ballister, they say in the context of complements, we show that the equilibrium depends on the maximum eigenvalue of the adjacency matrix. If you look at the substitutes, this is the this 2014 Econometrica paper. The main point of the paper is we show that the property of the network that matters is the minimum eigenvalue. And it's not completely clear why we get conditions on lambda max, conditions on lambda min in these different settings. So the goal of the paper is to use variation inequality reformulation of the Nash to come up with a unified way of understanding these properties. And the properties I'm going to focus on are mostly existence and uniqueness, but I'll say something about convergence of best response dynamics and comparative statics at the end. So we'll see that our framework allows study of general strategic interactions. I don't need to restrict myself necessarily to complements and substitute settings. And I will basically be able to, through this approach, also cover cases where strategies are multidimensional, not just single dimension, as well as constraints. So you can think about budget constraints or things like that also embedded in this framework. And I think the sort of one sort of goal of the paper is to provide a systematic understanding of which of these spectral properties matter when characterizing equilibrium or when establishing fundamental properties of equilibrium. So quickly, related literature, there's a large literature on social and economic networks, but our paper is also clearly related to the literature that use VIs in generic games. There's the Rosen's paper, which is not quite saying, this is the uniqueness, the paper that we use for establishing uniqueness, 65 econometrica paper. It doesn't say it uses VIs, but I'll argue that that's what he does. He uses really VI analysis to establish this uniqueness property. There's also the seminal work of Fakina and Peng. There's some recent paper which is buried. From the title, you don't understand that this is actually what they're doing. It's about communication games, so there's a lot of nice results in that paper. There's also large literature on aggregative games, some of them in social science, economics, mostly focusing on comparative statics, this monotonicity results, some of them thinking about distributed dynamics. And there's also large literature on traffic and economic models. I mean, this is sort of Smith's VI characterization of equilibria, following Beckman, Maguire, Winston, but also Dafermos. There's a beautiful proof that has been already referenced multiple times of Jose, Andreas, and Nico using VI to characterize price of anarchy results, as well as Nagurny that goes into comparative statics. There's also two recent papers that I would like to highlight that looks at a VI approach for study of special games, scalar, symmetric, substitute, but these are also looking at lambda min. And my goal will be to show that these different lambda mins, lambda maxes, and others can emerge and see how we can relate those conditions. So let me dive in, because I have little time and I guess too much to cover, so I'll try to do the best to give the main ideas across. So we consider a network game which is defined by n agents interacting over a network represented by this weighted adjacency matrix G, and Gij is basically represents the influence of J's action on I. And we assume that this graph is nice, there's no self-loops, the diagonals of this matrix is all 0. Now, what is the game? Each agent I chooses a strategy, multidimensional strategy xi, in his feasible set, this calligraphic xi, to minimize his cost ji. I'm going to be minimizing. So Francesca reminded me we're engineers, so we're going to be minimizing. So he basically choose xi to minimize his cost, which depends on his own action. Remember when I was saying what it depends on, as well as this local aggregator zi, which is basically aggregating actions of everybody according to this Gij network structure. Of course, goal is to compute the best response against this against this aggregate, and we all know the Nash equilibrium definition with the caveat of we're minimizing here. So, basically it says profile at which no agent has incentive to deviate, no unilateral deviations can improve the payoff or, reduce the cost in this case. I get very confused with this cost business. Anyway, so let's look at quickly where VIs come here. This is Nash equilibrium. It's a fixed point. We know there are multiple reformulations. VI, I will argue that the VI reformulation is powerful. And let's see what VI is, variation inequalities. The definition, general definition, is that X bar solves a variation inequality of operator F, constraint set X, if and only if this weird condition holds. F of X bar, inner product with X minus X bar, greater than or equal to 0 for all X. And I forget this condition all the time. So the way I remember which way this inequality goes is immediately related to optimization. So if we think of this F as the gradient of a convex cost function, it's not too hard to show that this definition, x bar being a solution of a variation inequality, is nothing but x bar being a minimizer of this cost function j. Why? Because if you think about the optimality conditions of this problem, this is just a stationarity condition for optimizing a convex function over a convex set. And if you forget this, you just immediately draw this picture which says that at the optimum, the gradient makes an angle which is less than 90 degrees with every feasible direction. So that's basically the equivalent condition for a convex optimization problem. So let me now put it back with the games. We'll have the following assumptions. Xi, the strategy sets are closed convex. For this talk, I'll assume boundedness. The paper has no boundedness assumption. It makes conditions a little bit more technical, but everything goes through. And then we assume convexity in your own strategy Xi, and we assume that everything is nicely smooth so that I can talk about gradients and Hessians. And if you remember this sort of optimality condition, and remember Nash equilibrium was one whereby every agent minimizes their own cost function with respect to their own strategy, right? I can basically put it together through this game Jacobian whereby I stack up all the gradients of ji's with respect to their own strategies and come up with an equivalent definition of the Nash equilibrium, whereby it's a Nash equilibrium if and only if x bar solves this variation inequality defined through this vector in which it's a weird vector. It's a gradient for each agent, gradient of that agent's cost function with respect to his own xi, because that's what he's optimizing. The thing to notice, I think that's perhaps a key idea if I can't get through everything, is that this formulation is valid even when this f is not integrable, meaning that this allows us to study games that are not potential. And that's sort of why we're able to address mixed interactions, because the literature really goes through this potential representation, does this quadratic structure, put some conditions on the signs so that it's a potential game. This doesn't need that. So that's one key idea. And the other thing is to notice is that Nash equilibrium properties, let's not worry too much about the constraints, that depends on the properties of this game Jacobian. So let's look at what that game Jacobian looks like. So the properties I'm going to talk about are things like this, sort of three properties which are in decreasing order of strength. So I say that f is strictly monotone if it satisfies this condition. And this is exactly thinking about f, and along this direction x minus y, it's increasing. So that's strict monotonicity. This is an inner product. If you think about all the blocks that you're adding for this inner product and assume that one of them is positive, that's called a block P function. And then if you assume that one of the components is positive, that's a P function. So remember this FIs are all n-dimensional because we're doing multidimensional strategy sets. So that's why there's a difference between these two. If n was equal to 1, this is the same thing. So this is an inner product of summing up all those terms, and strict monotonicity requires that sum to be positive. This requires only that there exists one term that's positive. So clearly, if it's strictly monotone, if the sum is positive, there exists a block which is positive. And if there's a block which is positive, then there exists a component for which the product is positive. And if n is equal to 1, this is it. So why am I interested in these? Well, this is the result from 2003. If any of these conditions hold, the variation inequality and therefore the game has a unique solution. Okay? So as you see, these properties dictate whether or not there exists an equilibrium, there exists a unique equilibrium. And the proof, let me skip, but this is exactly Rosen's proof. You say, for those who know the paper, just let me quickly flash. You get two equilibria, you put them into variation inequality characterization, you manipulate, you use strict monotonicity to arrive at a contradiction. So what Rosen does is a VI proof. So what am I going to do with this now? Here's the roadmap, or the idea of the paper. I will derive sufficient conditions for this game Jacobian properties that I've just alluded to in terms of the gradient of that game Jacobian, because they're easier to work with. And then I will basically look at network games and then show that this gradient has a nice decomposition for network games, whereby I can see the own effect, others effect, and network. Because of those decomposition, we can derive sufficient conditions for the properties of this gradient in terms of the network as well as the cost functions. And then from there, we'll go to the properties of f. And then from there, we'll go to the properties of Nash. So that's what this paper does. OK, let's dive in. So what are sufficient conditions in terms of the gradient? Remember, this was the properties we were interested in, strictly monotonicity, block P as well as P function. So claim is that, let me start from here. Strict monotonicity is equivalent to the gradient being positive definite. Equivalent.
Not symmetric. Oh, you mean, okay. Yeah.
No, not necessarily. Good. Yeah, good question. Yeah, so I put here some proof why this is true. I don't think we need to go through it. This is a result of Fakenai and Peng, but just quickly so that I think it's useful to keep it in mind. If you think about the linear case with the gradient being A, strict monotonicity, if you write it down, is nothing but a positive definiteness condition. And then similar with P function. Now, I guess the hardest part of this talk will be, as well as the paper to absorb, is this. So what is a condition for block P function? So let's just, before going into that, strict monotonicity is this gradient matrix being positive definite, and P function, for P function, we have a sufficient condition that gradient of F is a P matrix. And there's a gazillion definitions for P matrices. The one that's useful for our proofs is that positive definiteness is that quadratic form being positive, and P matrix is a weaker condition that only one of them need to be positive. Okay? But there are other things that you can use to check a P matrix. You look at principal minors, you look at the positive parts of the eigenvalues, and so on and so forth. So block P function, that's what is a sufficient condition for that. And this paper actually has that sufficient condition, which says that a matrix gamma, which is related to this gradient matrix, should be a P matrix. This is very, I think, unintuitive at first sight. And this gamma is nothing but, you get this matrix A. Remember, this is multidimensional strategy sets, meaning at each, this consists of blocks. Gradient with respect to xi, this is one block. Gradient of xi and xj, these are blocks. So what this gamma does is, for each block, represent a summary statistic of that n-dimensional object, meaning for the blocks on the diagonal, it takes a lambda min. For the off-diagonal, takes the norm and takes a minus. And when you see this for the first time, you're like, why? This is very unintuitive. And I think this that's why we put this block, how it relates to block P function to sort of motivate this condition. And this is the following. Remember, block P function was this inner product for an I to be positive. So if you write it down for this linear case, you can actually expand it out this way. And then you pull the diagonal and the off diagonals. And then you come up with lower bounds for each of these terms. So this part you can lower bound because it's a quadratic by lambda min. And this part you do Cauchy-Schwarz, and then you do this minus of this aij's to bound this part. And when you put the lambda mins and minus a's into the matrix, it actually boils down to this object being a P matrix. So it's a technical object that allows us to say to establish a sufficient condition for this n-dimensional structure. I hope that is clear. So this is a little different than the other two, but I mean, I think it's an object that allows us to get these sufficient conditions for the n-dimensional strategy sets. So, okay. Let's now look at the gradient of F in network games. What does it look like? Well, F is this object, remember, where I put all the gradients of ji's with respect to their own components. Now, if you take the gradient of that, you get this. I put it here. It's a little bit hard to parse, maybe, but it's just a, you take that object and you take a gradient. And what does it look like? Well, you take J1, X1, you take X1, X2, Xn, you take J2, X2, X, so on, right? And then Zi's, remember, were the aggregators. So let's look at what this looks like. Diagonal blocks are, take Ji, take the Hessian. And remember, Zi does not have Xi. There were no self-loops in our function. So it's only something that depends on the first component. And if you look at the off-diagonal blocks, Xi and Xj, what is that? Well, that's the gradient Xi Zi, and then the gradient of a Zi with respect to Xj, which is this Gij. So when you put them together, basically it has this nice decomposition. You can write the gradient F in terms of player's own effect. How does my own action affect my payoff? How does this aggregate affect my payoff? Because I'm in this network, how does the aggregate affect my payoff? And what does the network look like? So this now will allow us to isolate the effect of the network in these properties. Okay, so this is own effect, network effect, and the network. I will skip this. So this is what the literature considers linear quadratic games, where you have this quadratic cost, puts conditions on these KIs to have this best response monotone. But basically, the gradient is simple there, and that's what they work with. Whereas now, we work with basically something very similar. Similar decomposition, but does not need to be linear anymore. Okay, so now I'm going to basically talk about how we establish conditions for the network games that establish or that allows us to get these conditions. Okay, so let's look at the first one first, strictly monotone. I want to establish this game Jacobian to be strictly monotone, or equivalently, the gradient to be positive semi-definite. And remember, the gradient has this decomposition d plus k times the network. So I can do that by just saying, okay, let me look at its lambda min, right? Positive definiteness is basically the minimum eigenvalue being positive. And what does the minimum eigenvalue look like for network games? It's the d of x plus this Jordan form here. And then this lambda min, I can bound it from below by minus the spectral radius. This is symmetric. So because it's symmetric, the spectral radius is equal to the 2 norm. Now I can decompose the 2 norm into k and g. And I have a condition in terms of own effect, local effect, and network. If I can establish this being positive, I have that this operator is positive definite, and therefore it's strictly monotone. Okay? So basically, this is what this motivated us. Consider conditions of this form for network games: own effect, others effect, and something about the network, W of G. And what could this something be? Well, it could be G2, it could be lambda min, it could be G infinity. And the minute you put these sufficient conditions in one page, you get essentially everything in the literature. You get that for the first condition, the results of ballaster without requiring any strategic complements assumption. You get the condition B gets this Aluk result for substitutes. It generalizes it. It doesn't have to be the specific functional form they're considering. And this condition C is new. Nobody considered G infinity before, but we thought it's reasonable. Why? Because G infinity is the maximum row sum. What are the rows? The effect of others on me. So this is maximum of that, is maximum influence that an agent can have. So a condition of that sort also makes sense to study. Okay, so I'm doing not well with time. I knew this. So the other question that sort of we tried to understand was, we have now 3 conditions. How are these related to each other? Which one is more general? Which one is 5 minutes? Okay, I'm good. Okay, so for symmetric networks, actually, I'll skip some of the proofs. I'm happy to talk or send the slides later. For symmetric networks, the interesting thing is the condition which is most general, meaning it covers the most, for the same network, most set of payoff functions is the one that's given in terms of min, right? So with 2, you can establish positivity in a narrower class of games than in min. So this is sort of one way of relating the conditions in literature, but this is for symmetric networks. For asymmetric networks, you can't define lambda min, right? We don't have that the spectrum is real. But you can still talk about G2 and G infinity, and one can show that actually in some games you get the property through alpha 2, and in some games you get it through alpha infinity. So this allows you to get sort of a way of getting these uniqueness existence results for a larger class of games that has been studied before. But I think important point is to realize that conditions come from this decomposition of the network game gradient and takes this form of own effect, others effect, and network. So that's the lesson. And now let me just do probably 1 or 2 things. The next thing is to fill out this table. Put your alpha 2, alpha infinity, and alpha min, and see which one actually establishes these different conditions, strict monotonicity P function and block P function. I've already showed that if alpha 2 is positive, we get strict monotonicity. The next thing is to look at these 2 conditions, and then it's not too hard to show that those were more general. Alpha min in particular was more general. That doesn't establish strict monotonicity. For strict monotonicity, you need to lower bound this object. And sufficient condition for that is to bound both G infinity and G1. So if you just establish that one of them is small, it's not enough to say that the operator is strictly monotone. And you can, this is very vague intuition, but you can come up with examples that shows that these are not enough to establish strict monotonicity. And then we have sort of these other conditions, which I won't have time to prove, but it's not too hard to show that now if you look at this particular property, you can show that 2n infinity achieves that, but the min is still not sufficient to establish this property. I'm going to skip the proofs. The proofs are nice, but I'm going to skip. I don't have time. So if you look at the weakest condition, which is the gradient being a p function, now you can show that indeed this alpha min condition, which is the most general for the networks, is enough to establish not strict monotonicity, not this condition, but a p function property, which is enough to say that this game has a unique equilibrium. Okay, so this was the goal of the paper, basically. Fill out this table. Find conditions in terms of the network and other properties of the game to say that when do we have the properties of the game Jacobian to establish properties of the Nash equilibrium itself. Now let me, starting from this table, tell you a couple of things about the Nash properties that we can establish here. So I've already shown you the results from VI, Fakinai and Pang, which says that if you have any of these conditions, you have existence and uniqueness. So it turns out that any of our conditions give us existence and uniqueness. Second, this paper Scutari that I mentioned looks at asynchronous best response dynamics and shows basically that this gamma is a p-matrix condition is a sufficient condition to get convergence for this asynchronous best response dynamics. So looking at our table, it shows that alpha 2 and alpha infinity, which is enough to establish gamma is a p-matrix, gets us the convergence, and this one isn't. And let me tell you one thing which is very non-intuitive, still I don't understand. You would think that strict or strong monotonicity is enough to establish best response dynamics convergence. It isn't. You can construct counterexamples that says that strict monotonicity does not allow you to establish block contraction of that operator. So the relevant property is that gamma being a p-matrix. And that is something interesting to look at a little bit more. I'm not sure I understand that very well. And the other things are basically also, if you look at this Lipschitz continuity, sort of how does, suppose you have a parametric game, you introduce a shock to the game, and you want to understand how the equilibrium moves. So this is the comparative statics results. Either it's continuous, Lipschitz continuous, or how does the equilibrium move? Strong monotonicity is enough to establish Lipschitz continuity. We showed in the paper that block P function is also sufficient to establish Lipschitz continuity. So that allows us to fill this table with these different conditions and different properties of the Nash. I don't have time to talk about this, but I just wanted to flash a slide to attract your attention. You can also use these conditions to establish beyond Lipschitz continuity some differentiability properties. Sort of locally, how does your equilibrium move when you introduce shocks to the system? These are basically interesting in the context of cascades, systemic risk questions, and whatnot. And what we can show is that basically for a generic game with parameters or shocks, this strong monotonicity allows you to explicitly write down the change in the equilibrium in terms of the network structure, constraints, everything. And it allows you to study questions like, suppose you have a shock to the system, you can target one of the agents so that you minimize the effect of the aggregate level shock. Which agent are you going to target? And it turns out if you use that formula, immediately the agent that pops out is the so-called key player centrality, which is different from the Bonacci centrality that everybody uses. So you can use these conditions to be able to do such address such questions. So with that, let me stop. I'm glad I finished on almost time. So the goal is basically use VIs to develop an understanding. I think it's a very powerful approach. So all of these games are studied through potential functions. We don't need that. So that's the point of this paper. I mentioned in the paper we don't use compactness. That basically automatically generalizes Rosen. I have talked about the case, remember, with lambda min. I flashed out very quickly, but it was one dimension. Our result is only for one dimension in there. For the substitute case, we only have a one-dimensional result. We could not yet get the result for multi-dimensions. We have some partial results in the paper to address that. And for future, we have the multiple things we're working on. Asymmetry, using maybe other network measures here, thinking about sensitivity analysis instead of local. Can we think about how the equilibrium changes with respect to macroscopic changes? And the other one which we are excited about is this idea of a graphon game. And this is basically an infinite population way of modeling these large-scale games where you can still capture the local heterogeneities, not through the adjacency matrix, but through a graphon function. So, and that is something to talk about for later. So with that, let me finish. Thank you.
I guess a really urgent, quick question.
Yeah, so there's some literature, recent work on generalizing Rosen's results. It's Eitan, Altman.
Yes.
Do you have a comparison of this to that?
I knew that paper, but we haven't made the comparison. Good. Yeah, I haven't done yet. I know the paper. Yes.
Is it possible for you to incorporate coupling constraints of different agents actually?
I don't do that. Francesco, that's game theoretically, I think, a little bit problematic in my view. I don't understand what that means.
Okay, because you almost finished on time, maybe we'll take other questions offline.
And okay, thank you. Thank you.